So one of the major goals of introductory general chemistry is to explore quantitative relationships between reactants and products. And this pursuit is better known as stoichiometry. And this word is derived from the Greek and literally means change of substance. So in all cases in stoichiometry, the first thing we absolutely must have is a balanced chemical equation. So I'm going to use a hypothetical equation where I have A moles of A and B moles of B, and they're going to react and they're going to produce C moles of C and D moles of D. All the stoichiometry calculations will have the following in common. I am going to predict, given an amount of reactant, how much product I can make, which reactant I'll run out of first. So let's start making a list. So given that I have X moles of A, how much? And in terms of how much, we could answer this in terms of number of moles or the mass in grams or milligrams or kilograms. How much C or D can I make? How much B do I need? What is my theoretical yield, which by the way is this guy right here? What is my actual percent yield when I go into the lab and make this? And so these series of questions could all be asked in a problem. One or more of them could be asked in a problem. No matter how the problem is set up, the key physical observable in all stoichiometry problems is the number of moles. So moles is the key. And there are three different types of computations that you will encounter on any standardized examination. So this applies to the PCAT, this applies to the DAT, this even applies to the MCAT. We can be given the mass of a reactant, and we want to find the mass of product that is possible. I could be given one mass of one reactant and the other is assumed to be an excess, or I could have to determine which of those is the limiting reagent, which is which one runs out first. So I'm going to call that a LRP, a limiting reagent problem, in order to find the theoretical yield and also to find the limiting reagent. And we'll do examples of each one of these. So right now I'm just mapping out the kinds of problems that one can reasonably expect. Another type of problem that we could have is I am given the mass of a reactant and I want to find the mass of a second reactant or a third reactant or a fourth reactant. Also, I could be given mass of a product, and I need to find what mass of reactant 1 and reactant 2, etc., that I need to produce that product. The second type of problem that I can have is if I have molarity. When I have molarity, capital M, which as a brief review is a mole of solute over a liter of solution, or a millimole of solute over a milliliter of solution, or a micromole of solute over a microliter of solution, or an osmole of solute over an osliter of solution. That unit hasn't been invented yet, but it should, because it's awesome. So I can convert molarity times volume into the number of moles and then use the balanced chemical equation as before. That's the second type. The third type has to do with gas laws. If I have liters of gas, I know that at STP there are 22.4 liters of gas in 1 mole of gas. So notice that all 3 types of these problems have the commonality that the number of moles is needed to solve problems. Once I have the number of moles of a reactant, I gain access to the balanced chemical equation, and I can relate the moles of A to moles of C, or moles of A to moles of D. I can even relate moles of A to moles of B. So let's take a look at a few problems that fall under the umbrella of the first type of problem that I have rendered in green. So let's take a look at an example PCAT question in which we do the first type of stoichiometry problem. We are tasked with finding the maximum mass of H2O that can form when we have 4 grams of diatomic hydrogen react with 16 grams of diatomic oxygen. So what we want to do is to consider how much water can result from 4 grams of hydrogen. We're going to do this without considering the oxygen. We will get a numerical answer for how much water can form. Then we'll do the same process when we only consider the amount of oxygen. So we'll have 2 numbers that are in competition with one another. The smaller of the 2 answers will be the maximum amount that we can make. So let's go through the details of this. We have 4 grams of diatomic hydrogen. In order to gain access to the balanced chemical equation, I must convert grams to moles. This is done independently of the balanced chemical equation. We will only use periodic table values. We know hydrogen has a mass of 1, so H2 has a mass of 2. Therefore, 2 grams of H2, notice this goes in the denominator, so it can cancel, corresponds to 1 mole of H2. And the units grams of H2 will now cancel. This dimensional analysis bracket is really a series of fractions. So this is the same as 4 times 1 divided by 2. Now I have access to the balanced chemical equation, and I know that it requires 2 moles of H2 to produce 2 moles of H2O. This is done independently of periodic table knowledge. This is solely on the basis of the balanced chemical equation. Finally, I want to convert moles of my product to grams of my product. Once again, this is a periodic table conversion. I know that 1 mole of H2O is equivalent to 16 grams of H2O. Oxygen has a mass of 16. Each hydrogen has a mass of 1. 16 plus 1 plus 1 is equal to 18. And finally, I can cancel moles of H2O. So notice my final unit is in the unit that I am seeking. I want grams of H2O. I can now cancel out some numbers because I have 2 on the top, 2 on the bottom. That becomes 1 over 1. I have 4 on the top, 2 on the bottom. That becomes 2 over 1. So at the end of everything, I have 2 times 18, that is 36 grams of water. Now when you're doing a multiple choice question, this is very important. 36 grams represents the biggest the answer can be. Because if for the second part of this calculation, I have an answer that's bigger than 36, I take the smaller of the two values. If my second answer is smaller than 36, then I take the smaller answer that is less than 36. So when I look at my answer choices, and let's do that right now. Choice A is 18 grams. That is possibly correct. B is 36 grams. That is possibly correct. C is 54 grams. That cannot be correct. And what is cool about this, in my opinion, is that I've eliminated an answer by only doing half the work on the problem. And then, of course, D is 72 grams. Again, that cannot possibly be correct. So we need to go to the other half to distinguish between answer choice A and B. So let's do that. Here we have 16 grams of O2. There are 32 grams of O2 in 1 mole of O2. Again, notice that grams of O2 now cancel. I've now gained access to my balanced chemical equation. I know that 1 mole of O2 will produce 2 moles of H2O. Again, 1 mole of O2 goes in the bottom so that my units can cancel. 2 moles of H2O goes in the top. And finally, I know that 1 mole of H2O is 18 grams of H2O. Again, that comes from the periodic table. And now 16 over 32 is the same as 1 over 2. And 2 over 2 is the same as 1. All I'm left with now is 18 grams of H2O. The two numbers I compare are 18 and 36. I take the smaller amount. So the theoretical yield and the answer we're looking for in this particular problem is A, 18 grams. This also answers a question that's not asked. What is the limiting reagent? The limiting reagent is the reactant that results in the theoretical yield. It must be a reactant. So our choices are between H2, which allows us to make 36 grams of water, or O2, which allows us to make 18 grams of water. O2 is the limiting reagent because it will produce the least amount of water. In another context, we will run out of O2 before we run out of H2. So let's do another example, and in many cases this one is even easier, although students have a tendency to overcomplicate this. We have a balanced chemical equation where we have 2 moles of A reacting with 1 mole of B to produce 1 mole of C and 1 mole of D. If we have 6 moles of A and we react them with 4 moles of B, how many moles of C could form? We're finding the theoretical yield. So let's start with A. We have 6 moles of A. And we are required to react 2 moles of A to produce 1 mole of C. This is 3 moles of C. So let me go back to the same logical inference that I made in the previous problem. 3 moles represents the biggest that this answer can be. Because if B results in more moles of C than 3, 3 is still going to be our answer. So we can now eliminate answer choice C and answer choice D. Let's actually look at B. We have 4 moles of B. And we know that 1 mole of B gives 1 mole of C. In fact, this gives us 4 moles of C. We take the smaller of the two answers, which is 3, and in this case, 3 is the credited response. Okay, so let's do one more and then we'll move on to the next type. Finally, let's look at this type of stoichiometry problem where we're looking at the combustion of butane. So we have 2 moles of butane reacting with 13 moles of oxygen to produce 8 moles of CO2 and 10 moles of water. We are informed in the problem that we produce 88 grams of CO2. What mass of butane must have reacted? So you make an assumption that oxygen is the reagent in excess. So our strategy will be to go from grams of CO2 to moles of CO2 to moles of butane and finally to grams of butane. This is a 3-step process. So step 1 is a periodic table or periodic table knowledge. Step 2 is the balanced chemical equation. Step 3, periodic table knowledge. Very typical stoichiometry problem. The only curve in this is that we're working backwards instead of forwards. So we begin with 88 grams of CO2. The molar mass of CO2 is 44, and notice that this is really convenient because I know that 88 divided by 44 is 2. So I can immediately reduce that. We have moles of CO2. I'm going to go ahead and reduce this 88 over 44 to 2 over 1. Grams of CO2 go away. From my balanced chemical equation, I know that 8 moles of CO2 react with 2 moles of butane, C4H10. Again, I can reduce 2 over 8 to 1 over 4. And I can further reduce 2 over 4 to 1 over 2. Finally, 1 mole of C4H10. Now remember, each carbon is 12, so 4 times 12 is 48, plus 10 is 58. That's 58 grams of C4H10. Moles of butane cancel. 58 divided by 2 is 29 grams. That's our credited answer, which corresponds to answer choice C.